Okay, so before we resume, I would like to make two short announcements. So the first one is about the seminars that will be running during the semester. There will be mainly two seminars every week. One on Tuesday, a regular seminar, and one on Thursday, which is called like a student seminar or a junior researcher seminar. And the person in charge of collecting your titles, your abstracts, and in charge of scheduling these things is Yvan, who is here, and whose email address is on the blackboard. So if you would like to give a talk and to tell us about your recent research, you should go see Yvan for the Thursday seminar. So that's one announcement, and the second announcement is a change in the schedule for this week. So unfortunately, Professor Chen couldn't make it here this week. So Aram Harrow has stepped in, and he will give the talk on Friday morning, the last talk in the morning, so 10:45. Okay, so now let me introduce unless Yvan wants to say something, no. so then let me introduce the next speaker. He's Yoshiko Ogata from Tokyo University, and she's going to speak about the class of asymmetric gap Hamiltonians on quantum spin chains and its characterization.
Thank you very much, and thank you for introduction. And I'd like to thank the organizer for giving me this opportunity to talk here today. And my title is like this, but I have 3 papers with the same title. And what I'd like to talk about today is, discuss about today is about the possibility of matrix product representation of ground state phase. So more precisely, I will consider translation invariant finite range interaction, and out of that we can consider dynamics on various intervals, namely finite intervals and right infinite intervals and left infinite intervals and full intervals. And my question is how is it possible to represent all of them simultaneously with some matrix product? Of course, this kind of thing should not be possible, so in general. So the question will be more like when it is possible. So that is roughly what I'm going to talk about. But as I expect that not too many people are familiar with the terminology I just used, so let me start from explaining about these things. So let me first start from ground state. And so let A be a sister algebra, and alpha a strongly continuous one-parameter group of automorphisms on A. And let delta be the generator of alpha. And a state omega on A is called alpha ground state if this inequality holds for any element A in the domain of this generator delta. So it may be a bit strange looking if you see it for the first time, but it has nice characterization and it's well accepted notion of ground state. And in particular, if we consider this very simple case that is n by n matrices given by this self-adjoint element by this Heisenberg representation, then we get usual ground corresponding to the lowest eigenvalue. Then the state omega is alpha ground state in the previous slide sense, if and only if the support of this state is under this lowest eigenvalue spectral projection. So from this we can see that the definition in the previous slide can be regarded as a generalization of usual this finite dimensional case. So this latter thing is something we feel that it is ground state, but as it says that they are equivalent, we can see that the definition in the previous slide is the generalization of this finite dimensional case. So it's rather understandable. Now I would like to consider ground states on quantum spin chain. So let me introduce my system. So let n be some fixed natural number, and I consider a quantum spin chain is a shift algebra given by this infinite tensor product of L by N matrices. And then here there is an obvious action of tau of Z on this quantum spin chain, namely just shift. Well, if you write it in this equation, it will be like that. But anyway, there is shift. And I denote it by tau. So, and I call it space translation. And furthermore, for each subset lambda of Z, we can consider a tensor product of n by n matrices along this lambda, and we can regard this naturally, they are naturally regarded as a sub-algebra of this full chain. And in particular, in this talk, I will I would like to care about this right infinite chain and left infinite chain, and I will use these notations. Now, I would like to introduce the dynamics on this quantum spin chain. The dynamics I'm going to talk about is translation invariant dynamics given by translation invariant finite density interactions. So, so what it is? So first we fix some natural number m and some self-adjoint element in this local algebra. And then the local Hamiltonian associated with h on a finite interval I is defined by this formula. So what it is? Here, because the tau is the space translation, so tau x h is the translation of h by x. So some copy of h translated by x. And we sum up all the translation, such copy of h inside, fitting inside of this finite interval. And as a result, we obtain some HIH, which is local Hamiltonian. And from this local Hamiltonian, we define the dynamics on this finite shift algebra by this usual formula, Heisenberg representation. So like this, we already obtained some dynamics on this finite interval. I also would like to obtain dynamics on infinite intervals. So I will take the thermodynamic limit. So here it is. First, we consider the dynamics in the bulk. So let H be a self-adjoint element as before. And then for any A in the shift algebra in quantum spin chain, and any time t, this limit exists. So this was in the previous slide, it was dynamics in the finite interval, but I take the thermodynamic limit of this. And what is known here is that this kind of limit exists. It's not trivial, but it is well known that it exists. And it's defined as a strongly continuous one-parameter group of automorphisms alpha h on on the quantum spin chain. And I do the same thing to half infinite chains. Namely, for right infinite chain, I define dynamics like that, and left infinite chain, I define dynamics like that. Here, I is only on the right infinite. This finite interval which close to the infinity is only the one lying on the right infinity. So we can define this kind of, like this we can define 4 kinds of dynamics. So we obtain 4 kinds of dynamics on various kinds of intervals. And so once dynamics is obtained, we can consider the associated ground state, which is defined by the first in the first slide of this talk. And the question I would like to ask here is how they look like. And so this is a question I would like to ask. But I don't do this for full generality, and it actually gets less and less general as I continue. But anyway, so I would like to think about it, but we consider this problem for gapped ground state phase. So what I mean by that is the following, that I consider interaction H which satisfy this condition. So what is this condition? It's definition of gapped Hamiltonian. So Hamiltonian HH associated with H is gapped with respect to the open boundary conditions if the distance between the infimum of spectrum of local Hamiltonian and the rest of the spectrum of this local Hamiltonian is uniformly bounded from below by some gamma. So this sigma indicates a spectrum as usual. Recall that the local Hamiltonian is just matrices. So of course there is a gap, some gap between the lowest eigenvalue and the second lowest eigenvalue. The rest of the spectrum, there is always some gap. But the point here is that this gap should be bounded from below, independent of n, uniformly in n by this gamma. That is the requirement. And I would like to consider this how they look like question to this gap ground state phase. So it looks, sorry. So I'd like to consider this question, but we don't need to start from nowhere. Actually, there are many nice hints from which is a matrix product state. So let me next explain what is matrix product state. First, prepare n tuple of k by k matrices. So matrix product states are states given as follows. First, prepare an n tuple of n by n matrices V and natural number m. Then fix some, I also fix some also normal basis of Cn, which I write as psi mu. And then I define a map from k by k matrices to m tensor of Cn as follows, like this. So here there is a k by k matrix X, and for this I consider this kind of trace, and then we get some scalar, and I decide the quotient of this one is this scalar. So it's quite simple formula, and it defines some linear map from k by k matrices to this m tensor of Cn. And the state given by vectors in the range of this map are called matrix product states. But actually, any vector in finite dimensional system can be given by non-uniform matrix product states. So non-uniform means here I wrote uniform version, so V does not depend on the site, but we can consider the version that this V depends on the site. Then if we allow such a thing, then any vector can be represented like that. However, the size of these matrices can be huge. It can grow with the exponential rate of this interval m, interval size m. Okay, but if we consider only about a gapped system, the situation is not that bad, and that is the corollary of Fermat-Hastings area law, and here it is. And if the local Hamiltonian is gapped and the ground state is unique, then the ground state can be approximated by matrix product state on the shift algebra with matrix size of polynomial n. So it doesn't grow with exponential rate for the interval size. So that is so the gapped system is rather nice in this sense. But the question I would like to ask here is rather more conservative. This is very nice for sure, but the question I would like to ask is more conservative one here. So I would like to know when these ground states are exactly matrix product states. And what I would like to do is to represent the ground state on finite intervals as well as infinite intervals simultaneously. That is what I would like to do. And the question is when such a thing is possible. Of course, not all gapped Hamiltonian can satisfy such a representation. Allows such a representation, but the question is when such a representation can be possible. so that is a question I'd like to ask. But if we restrict our attention to only to the bulk, that is, we consider only the full chain, then this kind of thing is no. This kind of thing is no. So here is a theorem by Matsui. It says the following. So it says that for some interactions, the ground state allows matrix product representation. So how H is positive, and suppose that there exists a constant D such that this condition holds for all n. And so what is this inequality? First, you recall that we are considering positive interaction, and so this local Hamiltonian is the summation of positive things, and here we are considering kernel of such summation of positive things, and we are considering a dimension of that. Therefore, and the dimension of that. So the left side inequality means that this kernel is non-trivial. It immediately means that this the lowest eigenvalue of this local Hamiltonian is 0. And that is what, and this is a condition so-called reflex. Unfortunately, I have to, we have to live in this world. Anyway, we assume, he assumed this condition. And so as I said, the lowest eigenvalue of this Hamiltonian is now 0 from the left-hand side. This kernel corresponds to the ground state space. And so this dimension is the degeneracy of the ground state space. And the right-hand side says that this ground state ground state degeneracy is uniformly bounded from above for n. That is the second inequality. So suppose our interaction satisfies such a condition. And let omega be a translation invariant pure alpha H ground state, so let omega be a ground state of this H, such H. Then Matsui shows that the state omega is a matrix product on the quantum spin chain. So, so that is his theorem. So I explained before about the matrix product state on finite intervals, but I didn't for the infinite intervals. I don't know how much I have time, but I would like to skip this slide if you don't mind. And so let's say you don't mind. The only thing I would like to say here is that, like for finite interval matrix product state, there is some explicit formula for infinite version of matrix product state. That's what I want to say. So out of in a tuple of matrices, we can construct some state on the infinite chain, very complete, explicit way. Okay, so first looking at just this condition, we don't see we don't see any V here. So we wonder where this V come from. But it comes from something probably operator algebra knows well, and that is, let H be a separately infinite dimensional Hilbert space, and let n be natural number. Let phi be the unitary endomorphism of V of H, such that the commutant of the range is isomorphic to Mn. Then there exists a representation of Kunz algebra, so SIs, satisfying this condition. And this given endomorphism is given by this form. So here is the source of the V's. And in the Matsui theorem, the situation we consider pure state and plus some other conditions, and we end up with the situation that we can apply this theorem. And like that, he obtained some SI, but it's not matrix yet. But here is some remark here about that. And the n tuple V generating the matrix product state omega in the previous theorem is given as a restriction of SIs to suitable subspace. And there was this strange condition, right? So this condition includes about the kernel of local Hamiltonian. And this condition is used to guarantee that this subspace is of finite dimension. So that's how these V's have popped up. Okay, so coming back to this theorem, I still would like to make further remark about this theorem. First is, so this theorem says that this ground state is matrix product state. So there exists some n tuple of matrices which represent omega as matrix product. However, this n tuple generating this omega is not unique. However, it is not unique. But if Hamiltonian is gapped, we can choose primitive V unique up to some unitary equivalence plus phase factor. That is proven by Hannes, Nachtigall, and well now. So primitivity is something we saw from yesterday's Professor Felix Garcia's open session talk. I would like to introduce another characterization of same primitivity here, which I wrote here. We say V is primitive if for m large enough we have this condition. So what is this condition? But first I'm defining this strange curly MV as span of m tuple of V's. So M is fixed. So we consider always m tuple, m monomials of V's. We consider always m monomials of V and consider the span such. And this is, I denote it by KMV. And the primitivity requires that, so this is clearly subspace of K by K matrices. And the primitivity requires us that this KMV, as M goes, M gets bigger, it gets saturated and it gets saturated to full matrix. That is an equivalent condition of primitivity. And so I would like to use this condition because it will come back again in this talk. Anyway, so this is primitivity. Coming back to this remark, so this I was saying that the matrix shows that the ground it is in this setting is matrix product state, but it is not unique. But if Hamiltonian is gapped, we can choose primitive V, primitive distance, unique up to unitary equivalence and plus phase factor. So if V and V prime both generate the same matrix product state, then they should be related to each other like this. So here U is a unitary and exponential IC is a phase factor. So what we have so far is the following. We started from interaction, positive interaction satisfying these kernel conditions, and we assumed furthermore, we assumed that Hamiltonian is gapped. Then we somehow, thanks to Matsui, actually this there is converse to this story. Historically it was this and that, but anyway, there is converse to this story that is a famous paper of Hannes, Nachtigall, Werner. That is, if V is primitive, then there is an interaction, positive interaction generating a gapped Hamiltonian whose ground state is a matrix product state given by V satisfying this condition. So these gapped and these properties about kernel and something we started from, but we can go conversely. So if we starting from primitive V's, we can obtain some interaction satisfying such conditions. But I also would like to specify what is this interaction HV which satisfies these nice conditions. And here is the definition of it. It is defined in terms of the gamma we have seen before, the linear map from K-by-K matrices to tensor of Cn. And the interaction HV is given by the orthogonal projection onto the orthogonal complement of this range of lambda gamma mv. So it's whatever the definition is, that I want to say it is very concrete way of defining interaction. So again, let's see the situation. Our situation is that ground state on the full chain of these two interactions are same. The first interaction is some interaction satisfying these nice properties, but qualitative properties. And second one is very, very concrete. It is made by out of primitive n-tuple of matrices. And the thing I would like to so we see that this corresponds, but only for the full chain for the moment. And the question I would like to ask today is that can we extend this correspondence to other intervals? And I would like to represent these things simultaneously by some primitive V. So here I simply would like to replace this full sister algebra, but I would like to add these three things to here. That is the question I would like to ask. So is it possible to find some primitive V satisfying this correspondence for also not only from full chain but also for these other intervals? But unfortunately, the answer is no. This is because there can be edge mode which cannot be taken care of by primitive V. That is discovered by Bahaman and in the model called PVBS model. And more precisely, in this model, the ground state degeneracy on the right infinite chain and left infinite chain can be different. But if we consider only primitive case, this ground state degeneracy on the right infinite chain and left infinite chain should be the same. So there is some phase we cannot capture just by primitivity. So we have to go beyond primitivity. And the question is if there is a correspondence between, repeating what I would like to do is, the question is if there is a correspondence between ground state on AZAR and A0n minus n of this interaction H satisfying this kind of thing. We have the qualitative property we have seen so far, and some HB for interval matrices. But we now know that we cannot use primitivity here, but it should satisfy some property. So what is and so yeah, I'd like to replace primitivity with some property. But actually, I don't know if this is possible, unfortunately. But I know it is possible if I do add two more conditions to this list of the list in the list of property in A. So let me do that. So I add two more conditions to A. The first one is exponential decay of the boundary effect. So let Gn be the spectral projection of local Hamiltonian onto the lowest eigenvalue 0. Then I consider out of this spectral projection Gn, I consider the uniform distribution over this Gn. This is represented by this trace thing. And the requirement here is that this uniform distribution converges to some state on the right infinite chain exponentially fast in this sense. So I'm considering some n intervals, and I'm measuring here by A. And actually there is other edge. But as we are localized here, we don't realize the existence of this edge too much. And that is the requirement. And furthermore, this state that this uniform distribution converges to should have good property, namely if we consider the reduced density matrix of this state, then I don't want the spectrum of it to have too small eigenvalue. So it's too small non-zero eigenvalue. So this is, it seems to require something, but actually I expect that this the interaction H should satisfy this kind of condition anyway, this kind of property anyway, if the ground state structure can be represented by matrix product state. And I think that is the limit of the matrix product state anyway. Yeah. Okay. So the previous one, I think it's rather necessary. But what I don't know is that there is still possibility that this condition can be derived from first three conditions. That I don't know if it is the case. Probably not. Anyway, second one is rather technical condition. This is more technical condition asked for the simplicity. We can remove it, but then the object I will show in B can get more tiring. So I assume this for simplicity. Anyway, I hope I'm not asking too much here. So what I'm asking here is the following. For any ground state psi on the right infinite chain, there exists natural number n such that this condition holds. So here what I'm considering is such ground state and its space translation. And I'm considering the distance between them. So of course, as I am considering the distance between two states, so the maximum value we can take is 2, but I would like to ask at least for 1L, this is strictly less than 2. So I hope I'm not asking too much, but I don't know, it may depend on the person who's here. So anyway, I will add these two conditions to my list of properties of A. The question is, if there is a correspondence between ground state on the full chain and half infinite chains and finite chain of interaction H satisfying this list of properties, and HV for any tuple of matrices V satisfying some property. So now I have to specify some property. So here is some property that I call class A. So class A is a set of any tuple of matrices which satisfies the following conditions. First of all, my V's live in this tensor product. And second, I want you to recall that this definition of KLV that was just a span of L monomials of V. And third, I would like to ask you to recall the primitivity condition that was KLV should get saturated to the full matrix, KLV matrix for L large enough. And yeah, class A is a kind in philosophy, it's kind of this primitivity condition. So it gets saturated, but not to the full matrices, but to this object here. So what is this object? Here, this is just n by n matrices, but dV is some subalgebra of upper triangular matrices, and lambda V is some diagonal matrices, and we consider L power of it here. And YV is another upper triangular matrix, and we consider L power of this A1 plus YV. So it's not so not so bad. It's the understandable object, I would say. It's algebra, and it's just some L power of some fixed element. So the class A is an analog of primitivity, but it gets saturated not to full matrix, but to this as an understandable object. So that is this some property I would like to require for my n tuple of matrices, and out of such n tuple of the matrices, I define interaction as Farnes-Nachtwey-Wellner did before. As namely, we define the interaction HV as the orthogonal projection onto the orthogonal complement of this range of gamma. And here is the main result. And suppose that H satisfies the properties 1 to 5, then there exists a n tuple V in class A, which I just described, and satisfying the following. The ground state HH and HV on infinite intervals coincide. That's what I wanted. I wanted to represent all the ground states on various intervals by the same matrix product simultaneously. For finite intervals, I don't have exact representation. They are not exactly the same, but it's not so bad. So what I have is the second one. So let Hn and Hvn be projection onto the ground state spaces of this local Hamiltonian given by H and Hv respectively. And then I consider the distance, or we can consider the norm operator norm distance between these projections. And the statement here is that it gets closer and closer exponentially fast with respect to the interval size. So it's more or less what I wanted in the beginning. So we have this kind of representations. And furthermore, we have converse like the Farnes-Nachtwey-Wellner, namely starting from class A is a Hamiltonian we constructed from previous slide like this, satisfies these properties 1 to 5. So recall that starting from primitive V, Farnes-Nachtwey-Wellner showed that these nice properties 1 to 3 of this Hamiltonian given by this interaction. But I can do the same thing for class B. Okay. So I skip this. At the end of this talk, I would like to ask further additional question to question. So it's about symmetry. Suppose furthermore our interaction H satisfies some group symmetry. So let G be finite group, and let V be a unitary representation of G on Cn. And then we consider the action beta gamma of G on gamma, where gamma is this various kind of intervals given by just this infinite tensor product, so infinite finite tensor product. And assume that our interaction H is invariant under this action, in addition to 1 to 5 which we have assumed. So I'm furthermore assuming that this H is satisfied this condition. So there is something to do with a group for H, and I would like to know how we can see the effect to this class A. And so here is the theorem. Suppose that our interaction H is invariant under the action of G in addition to 1 to 5. Then there exists a projective representation U of G on CNV. So please recall that class A was this form, so this MV corresponds to left side. And projective representation WG of G on right hand side, and some one-dimensional representation of Xi of G satisfying these properties. First, this projective representation on the left side commute with this Y and lambda, which was defining the class A. And second, if we define a large UG by this tensor product, then if we adjoint this V, our class A element, each class A element like this, then we obtain the relation between because this large V was the defining representation. That was something which defined the dynamics on the representation on action of G on A8. So there is this kind of relation. Here it's maybe hard to read, but this Vg mu is a mu element of matrix Vg. So one remark is that actually the existence of projective representation U satisfying this last inequality and this one-dimensional representation satisfying this equality was already shown by Matsui. And question here is, as now we have some structure about class A, so we should clarify how it's related to each other, and it turns out it's factorized like this. And you can regard this U part as acting on the bulk and this W part acting on the edge, or something like that. Okay. I still have 1 minute, but that's all I want to say. Thank you very much.
Excellent. Are there any questions for Yoshiko?
I have a comment. I mean, I think that in phenomenal algebra, they have studied this problem when certain states are automatically tensor product states. There are kind of a number of theorems. It depends which will. It depends on the type.
Okay.
So there's something, you know, and then, but the other question I have is concerning if you have these finite, and therefore it's not surprising that if you go from an infinite interval to half an interval, they're not necessarily all tensor product kind of, you know, matrix product states. So the question is, have you considered doing dilation theory? So you have a small system, we dilate it in one which has full symmetry, studied in various states there and go back. This would be a very, you know, natural dynamical approach.
I mean, full
Okay.
Yeah, but you can extend it to a larger symmetry where you lose the finite dimension, but then by projecting back, you have a chance to get these, you know, projections on the finite dimension subspace. Have you tried these kind of?
No, I even.
It's very natural in the dynamical systems, but maybe not very natural here.
I would like to ask about it more later. Thank you.
So if you write down an interaction, there's always an ambiguity. You might add a term at one side and subtract it on another side. That will give the same dynamics or the same formula, the same derivation actually, and then the same dynamics on the infinite volume system. So obviously.
Yeah.
So but now, so that these such Hamiltonians would then differ by boundary terms.
Yeah.
And your theory of boundary terms doesn't take that into account. You always want a parent type Hamiltonian. Right?
Yeah, parent. Yeah.
By the ground state, where you have a controlled ground state on a finite volume.
Yeah.
Could you imagine a theory of boundary terms that would be sort of naturally stable under that kind of addition of boundary terms?
I don't.
Could you recognize that you have a finitely correlated matrix product ground state, even if you have, I mean, independently how the H is presented, right? So even if you have added some boundary terms.
Yeah, I don't know. Well, it's not my opinion, but someone said that boundary is very subtle problem that you cannot imagine too much stability under evaluation. Yeah.
Other questions? If not, then let's thank you.